Welcome back to ECE 442-542. Homework number 4 is due tomorrow evening at 11:59. Exam number 2 is same time next week in this same location, same time and same location, but just 1 week from today. Our review session for exam number 2, I'm scheduling it for Monday, immediately following the lecture at 7 p.m. and I'm going to try to record that if you cannot make it in person, but sometimes it's helpful to have a live audience. I don't know if there's a game that night or not. If there is, I won't expect a live audience necessarily. There's a game tonight, isn't there? Maybe that's why the numbers are down in class. I don't know. Today what I want to do is talk more about translating design specifications into Z-plane pole locations. And those Z-plane poles are going to be occurring typically in complex conjugate pairs. And this is really to gain intuition into when we start the design process, somebody might say, I need you to satisfy these particular design specifications. And it may be settling time, it might be percent overshoot, it might be time to peak, it might have other things. But right now we're worrying about these transient performance specifications. And we want to know where do we want our closed loop poles, the dominant closed loop poles, to live or be located in the Z-plane. And then we will design our controller to make those two poles dominant in our closed loop system. That's the big picture view of why we're talking about this. We need to know the connection between design specifications and dominant closed loop poles. And last time we tried to talk a little bit about that. And this is what I'm hoping you start to think or start to see when you're confronted or given particular design specs. And the Z-plane poles, a lot of times it's easier or maybe more straightforward to think about those in terms of the Z-plane, in terms of polar coordinates, a radius away from the origin and an angle, theta sub d. That's maybe the way to think about these complex conjugate poles in the Z-plane, as maybe not its rectangular position in the real part and imaginary part. Maybe you need to be thinking in terms of radial distance and angle. That's maybe an easier way in the Z-plane. For the continuous time S-plane, a lot of times it's easier to think in terms of your real part and imaginary part because that gives you your damping and your damped frequency of oscillation. But here, when we talk about settling time, T settle, that means we're talking about some distance away from the origin, this concentric circles, this bullseye. If you have a quicker settling time, what do you want R to be? Bigger or smaller relative to, let's say we now want to faster, we want to speed up our system so that it settles more quickly. Our T settle is smaller. What does that imply for R? It needs to be further inside the unit circle, doesn't it? The radius now needs to be collapsed. Just think 1/2 versus 1/4. 1/4 is going to, when you raise it to higher and higher powers, it's going to get smaller more quickly than 1/2 does. So the R needs to be smaller if you want a faster settling time. Percent overshoot. I want you to be thinking, and now this is the calculation or the equation, and you could be seeing this curve, but we'll just give you that expression that involves natural log of PO over 100 squared, etc., with pi squared, which is roughly 10 in the denominator. But the percent overshoot gives you a zeta. We haven't really talked about where that is in the complex plane or what that looks like in the complex Z-plane, a constant zeta curve. In the S-plane, it's a particular angle in the S-plane. In the Z-plane, we're a little bit late. We're a couple of weeks late. It's actually I should have presented this on Valentine's Day, but we didn't even meet on Valentine's Day. But it's sort of a squished heart shape. It's a heart on its side. It's a logarithmic spiral. So when you see this zeta, you might be thinking heart, if you need something to connect with, or Valentine's Day. And then you'll go, oh, percent overshoot, my heart. So that's zeta. We'll see that shortly. Peak time, that's how quickly do you reach your first peak, and that's sort of speed of response. That's this theta sub d, and that is an angle that you can pretty easily see in the z-plane. The quicker your peak time, the bigger that angle is going to be in your r at an angle theta sub d representation of these dominant poles. Those are the three transient performance specs that we talked about, and I want you to get comfortable with thinking of these in continuous time and discrete time. Here, just for a recap, here is our way of parameterizing the complex poles in the S-plane with the damping ratio zeta and the natural frequency omega sub n, and you may refer to those as this real distance into the complex plane being sigma, and your vertical distance being the damped frequency omega sub d, and your modes of oscillation are immediately obtained from this sigma and omega sub d value. Sigma gives you the exponential decay rate of this oscillation, and omega sub d gives you the damped oscillation frequency. Meaning, in the S-plane, if you have a pole and you have its twin down here, its conjugate, which I didn't draw to save space. I know paper's expensive, so I just gave you half the plane. But now you have this pole and its twin down below, and those give rise to this exponentially damped sine and cosine in general. That's what I want you to be thinking of, and you know the decay rate is influenced by the distance into the complex S-plane, the real distance to the left, and you know how fast you are shaking or vibrating. Your damped frequency is how far your imaginary value is in the imaginary direction. That's your frequency of oscillation. And you might, in the classical control setting, talk about an angle theta and relate that to zeta, but a constant zeta in the S-plane is just this at a particular angle. Zeta corresponds to a fixed angle. And what's a sweet spot for percent overshoot, zeta value-wise? Did I tell you that last time? Zeta of 0.707, 0.7 is what I round it to, a 45-degree line, an angle at 45 degrees. That's a sweet spot. That's a nice trade-off between speed of response and quick and overshoot. Zeta and omega sub n. And omega sub n in the S-plane is simply the distance those poles are away from the origin in the S-plane. That's your natural frequency, not the damped frequency. Now, if you had a zeta value of 0, then that pole rotates over and becomes, the damped frequency is your natural frequency, zeta is 0. Zeta 1, these two red poles rotate around and you get two real equal poles that are with a zeta value of 1, and they don't have any omega sub d, no oscillatory behavior. That's what happens in the S-plane for continuous time. We have our way of mapping those. Z is equal to e to the st, and if we use that same parameterized form for the S in terms of the damping ratio and the natural frequency, and split that into two pieces, you have one piece that has a real exponent, that gives you the radius, and you get another piece that has this complex exponent, that gives you your angle theta sub d. You now have r, which is, in this case, this is the z-plane now, but now you know the distance away from the origin is r, and that's influenced by zeta and omega sub n in the s-plane parameterization, and your sampling period, capital T. You also know what the theta sub d is. That's omega sub dt, and omega sub d is what we've already defined it, omega sub n times the square root of 1 minus zeta squared. But this is now your parameterized, and this has its twin, its conjugate, which would be e to the minus j theta sub d in the complex plane. So it's at the same radius, just the reflected angle through the horizontal real axis in the complex z-plane. You now have two complex planes to be thinking about, the s-plane and the z-plane. And that shouldn't be a stretch. That should be easy for you to do now. But this is now what we have to be thinking about. Oh, I didn't scroll up quite far enough. But now, this is why I said it might be helpful to think in terms of radius and angle. In terms of radius and angle, now the exponential decay is impacted by that value of r, the distance you are away from the origin in the z-plane. So if r is less than 1, now you have a stable, a collapsing exponential. If r happened to be bigger than 1, now you're growing, and it's an exponentially expanding sinusoidal response. And that's available to you also, or can happen. But now, if you know the radius and the angle, you can immediately write down the structure of your discrete time transient behavior. It's going to have a collapsing if r is less than 1, exponential behavior, and the way that it's shaking, or the number of points you have in each of these oscillatory periods, is influenced by this angle that that pole pair makes with the real axis, the theta sub d. That's your, and we want to be able to figure out where do we locate those. Those might be our desired closed-loop pole locations. They may not be where the system begins or where the system naturally wants to be. You have your open-loop poles. When we go into the control setting, we may want to move those open-loop poles to these closed-loop pole locations. And that's what's driven by the design specifications. The design specs, your boss, she's going to say, I need you to have a settling time of this, and I need you to have a % overshoot of this or less, and I need you to get there quickly, so I need a peak time of this amount. You go, oh, okay, I'll go back to my desk and I'll figure out where I need to be in the z-plane and where I'm starting at with my given system that I'm controlling, my plant. My plant may not naturally want to satisfy those design specs that you were given, and we need to then design controllers to make that happen. But first, we need to understand, how do we get these desired poles? And those are coming from the design specs. And here we're thinking of 3 transient design specs. Last time we talked about the settling time spec. And the settling time spec we've already talked about. That was first exam material, I think, right? You had this equation where if you were just looking at an initial condition response for a first order system, it would behave depending on how far away that pole was or where that pole was located on the real line. And that gave you your R. And we're just agreeing to, if you have a second order system, we're just saying just approximate that behavior with its radial distance, which is really that's influencing the decay rate anyway. But we now know that R raised to the n sub s, where n sub s is some number of samples that you want to accomplish your settling time within. That needs to get you to 1% of where you started, and that's this 0.01. This is a governing relationship. You might be given R, probably not. You may be given your settling time. In absolute time, then you have to divide that out by your sample period to figure out how many sample periods in sub s do I have to reach 0.01, and you may have to solve for R. Where do I want my poles? How big of a bullseye do I need to be inside of in order to satisfy my settling time specification? So this is what we, I think, derived at the end of last lecture. You might be given a settling time, a T settle. You can then find in sub s if you know what the sample period is. Maybe you don't know what the sample period is. Maybe somebody's giving you a generic. They say in sub s needs to be 10. You need to settle in 10 sample periods, and maybe you don't even, or maybe you're not told what T is. You could still use in sub s by itself. But if you now know in sub s, you can now solve for R. Meaning, given a T settle, that implies a particular radius away from the origin in the Z-plane by means of this quick analysis of finding the radius. The radius is simply 10 raised to the power minus 2 over n sub s, where n sub s is however many sample periods you want before you're decayed to 1% of where you started. Is that clear? That's one of the 3 design specs. So when you see or hear settling time, what do you think? What do you see? What image comes to mind? A bullseye, a target, concentric circles, right? So when somebody says settling time, you're thinking, I need to figure out how close or how small these concentric circles need to be in order to meet that design specification. How far away from the origin are my dominant closed loop poles? Maybe I should just scroll all day, huh? I should have done this before, but now I'm out. So now I'll have to slow down. But this is where we're starting. Now we want to talk about the percent overshoot. And the percent overshoot, if somebody gives you that specification, they say, give me a 30% overshoot or less or better. So now they want you to only go beyond 30% of where you finally end up. You can now, with this formula, calculate what your zeta value is. Or you could have on your paper, on your cheat sheet, this is exam 3 material, isn't it? Hint, hint, but don't check out just yet. This will help you, I think, as we get closer to the end, it will help you for exam number 2. Yes, sir. So the settling time, I was hoping, maybe I didn't include any of that, did I? Bummer. All right, so this, I'm getting to the punchline for the last thing today, but this is, I need this curve to answer your question. So the question was, settling time, how is that related to peak time or overshoot? Here is our second order system response of a system that's second order. It's a step response, and I've normalized it to have a final value of 1. Where's the settling time? The settling time occurs now over here, doesn't it? I want to know, when do I get within 1%, when do I get in this 1% tube of where I'm finally going? Meaning now my settling time is here somewhere. Let's say 0.3 seconds. When I reach steady state, that's my settling time. What's my overshoot? Well, I have to figure out where's my maximum value and when does that occur. That's my peak time. So my peak time is better be less than my settling time. So that's the relationship there. We haven't got to the peak time yet. That's the third design spec. But this is now the overshoot. What's the percent overshoot in this problem or with this particular response curve? 20%. I go beyond where I finally end up by 20%. So you take your peak value, you subtract your final value, and divide by your final value, and multiply by 100%. That gives you your percent overshoot. Did that help answer your question? So the percent overshoot, the peak time, and the settling time all are related to this particular plot. And it's all based on an ideal two-pole system in the S-plane, and it's a pure two-pole system. When I say pure, you don't have to think of ivory soap, which is 99.9% pure, but I'm meaning you only have poles. You don't have zeros. So the zeros don't exist. You don't have finite zeros in a pure two-pole system. That's in the S-plane, okay? This obviously is not the S-plane because of these jagged edges, right? This is a discrete time simulation. But I'm giving you the punchline before I even give you the joke. But this is where we will end up at the end of the day, maybe. Is that okay? Does that help answer or orient? Maybe I should have showed you this to begin with, then we could end with that. Then you understand the joke. A lot of my jokes you don't even understand. Sorry. But this one I think you get, right? This punchline, not much of a joke. Question?
So I'm not really understanding why sample period doesn't play a role in the number of. So for example, if you increase the sample period, what if that increase the number of people you get?
Well, now I'm really messed up. Where was I? So now what we are doing is essentially we are sort of dividing that sample period out in all of this analysis. So it's all relative to what's happening. A lot of times we just don't even show the sample period, but it does make a difference if you now say, I want a settling time of half of a second, then you need to know what's my sample period so I know how many sample periods in sub S it's going to take. So if you change your sample period, capital T, then this guy will change. Your R will change. Now, depending on how you're approaching that problem, you may or may not need to incorporate the sample period capital T in your calculation. Here, if you don't have it, it's actually sort of implicit in R, your sample period. So R, where did I have it? It's now e to the minus zeta omega sub n capital T, so it's buried in just this radial distance already. So it depends on how you want to think about it, but if you're given a time for settling in an absolute time sense in seconds, then you'll need to know what is my sample period before you start finding this capital N sub S. Okay? That help? So the question was, what happened to T, basically, I think. Where did T go? It's the sample period. You have to keep track of it, typically. Okay? Now, where was I? I was trying to discuss percent overshoot and how that relates to the settling time that we just talked about. And this percent overshoot is going to occur before you settle. This is going to be sort of where do you first bump. So the way I like to describe it is if you now have closed quarters and you have a flexible robot arm, or maybe it's not even that flexible, but now you need to go from point A to point B, and it's close to a wall, and you overshoot more than what you need to do, then you're going to have problems. So that might be one way of thinking about overshoot and not getting too much overshoot. Because if you're trying to get from point A to point B and you command it to go to B and your overshoot is really large, you may have problems. You may want to go quickly but not overshoot too much, and that's why we had that sweet spot. A zeta value of 0.7 gives you a percent overshoot of 5%, and that's not even hardly noticeable in that curve that I just had. All right, so now we have this relationship for percent overshoot and zeta. What we want to do is try to understand what a constant zeta line looks like in the Z-plane. In the S-plane, if you remember, well, let me just draw this. Remember our relationship, if I picked a point that this distance and then this distance so that if I now said cosine of theta is adjacent over hypotenuse. So for a fixed angle, that's giving you a fixed zeta value in the S-plane. So if you have a given percent overshoot, that's going to give you a fixed zeta. That zeta gives you a fixed angle in the S-plane. What we want to figure out is what does that look like when we map it through z is equal to e to the st in the Z-plane. So now let's see if we can understand that. We know z is equal to e to the st, but that's just e to the minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared t. That's the way we've parameterized S in terms of damping ratio zeta and natural frequency omega sub n. Now let's just break that into two pieces to where we have one piece that was real and one piece associated with the imaginary exponent, and that gives us our angle, so that we now have e to the minus zeta omega sub n cap t and e to the j and a lot of times I'm going to pull that t in front of the square root, just it's cleaner to write it that way. So it's omega sub nt. Maybe I'll just do that now. Where this piece is r, and this is now e to the j theta sub d. And what are we looking for? We're trying to fix zeta. So let's just fix a zeta value. That means maybe I fix zeta at 0.7. It gets fixed here, and it gets fixed there. But now, what do we have left to adjust? We have our natural frequency to adjust. And what does the natural frequency correspond to in the S-plane? The radius. So now the omega sub n, I want to look at what happens when I have different or higher values of natural frequency. As I march up along this fixed line in the S-plane, what's that going to map into in the Z-plane? Let me just see if I can sort of describe it here with some examples. Let's say we fixed zeta, and now what I want to do is, let's just say this is omega n sub 1, and maybe this is omega n sub 2, and this is omega n sub 3. So the n's increasing are going further away from the origin in the S-plane. If that's the case, then I can look at this parameterization and I can say what's going to happen to my radius and what's going to happen to my angle, because they're both functions of the natural frequency. If I look at my radius first, if I say, okay, R1 is now associated with omega sub n sub 1, this is now e to the minus zeta omega sub n sub 1t. And now I'm going to change that. I'm going to say e to the minus zeta omega sub n sub 2t, and r sub 3 is e to the minus zeta omega sub n sub 3t. And what's happening to those r's? How is R1, R2, and R3, how are they related for these increasing natural frequencies? Are they increasing or decreasing? So omega n is getting bigger. We're raising this to a higher and higher negative power, so the r's are getting smaller, aren't they? So now in the Z-plane, as I march up here, my radius is going to start getting smaller in the Z-plane. So keep track of that. I now have a relationship on my r's. I know that R3 is less than R2 is less than R1. Now let's see what happens to the angles. Theta sub d, 1, and for a fixed sample period, capital T, and a fixed zeta value, the only thing changing is omega sub n sub 1. Now, how are the thetas changing as omega sub n changes? And remember, theta sub d in this case could be in radians as a unit. Omega sub n sub 1 is smaller than omega sub n sub 2, and this scaling factor is the same in all of them, so I'm just increasing my angle, aren't I, as I increase the natural frequency. So if I picked this point, omega sub n sub 1, I'm going to have a certain radius and an angle. Then what's going to happen? I'm going to go to this point. My radius is getting smaller, but my angle's getting bigger. Then when I go to point 3, my radius is smaller and my angle's even bigger. Do you see what's happening? Do you start seeing this heart on your side? Maybe it's not clear, but let's just sketch it. This is what you're getting, and I won't be able to sketch this very well, but here's your Z-plane. You now have some curve that sort of does that. Meaning, at the first frequency, maybe you're right there. You have a long radius and a small angle. The next one, your radius is shorter and your angle is bigger. Maybe you don't like that shape for a heart, but it's a logarithmic spiral. So I used to give this lecture on Valentine's Day just to make a point. You know, I'd get everybody coming to class just to get this lecture. No. And then I have this point. But now you have a region, and this is associated with a fixed value of zeta. So this might be some fixed value. Now, can we look at the extremes? What if I had zeta equal to 0 in the S-plane? Where did that put our poles? Zeta is equal to 0. Zeta is, remember it's term, it's the damping ratio. Now you have 0 damping. If you have 0 damping, where are your poles in the S-plane? Right on the imaginary axis, right? Bless you. So now you have things on the imaginary axis which correspond to what in the Z-plane? What's the imaginary axis do? Can't see. I was going to put my glasses on and they don't have them. Now I can see faces. What do we have? We have the unit circle, don't we? For zeta equal to 0, we're on the unit circle and we're not decaying, are we? So we now have that's supposed to be zeta equals 0, unit circle. Let's look at the other extreme, zeta equal to 1. Where are we in the S-plane? Zeta equal to 1. Plug it in here, and it's related to this angle. When do we get cosine of something equaling 1? What's the something? What's the theta? It's 0 degrees, isn't it? So if this angle, if this pizza wedge gets really small, down to 0, if that angle is 0, zeta is 1. So now we have two real equal poles, and what's zeta equal to 1 look like over here? Which of these zetas is bigger? This one? And if you're listening to this, you haven't a clue what I'm asking. Sorry. Teach you to... All right, I'll behave. If this zeta versus this zeta, which is bigger? The blue, isn't it? Well, they're both blue, but the blue highlight, right? The yellow highlight is 0. So now as we increase zeta, what's happening to our percent overshoot? As we increase zeta, as zeta goes from 0 to 1, our percent overshoot decreases, doesn't it? And what's our heart doing? Our heart is getting smaller. It's collapsing towards what? The extreme value of zeta, which is zeta equal 1, the biggest value. This is now zeta equal to 1. It's a real value. It's on that real line between 1 and 0. That's zeta equal to 1. All right, now do we understand zeta values? We have the extremes, 1 and 0, and everything in between. And a zeta value of 0.7 is going to be a nice heart shape, kind of squished. But the reason I'm saying heart is because you have its mirror reflection down below. This, obviously, you're just seeing half of the heart. But we have a whole heart in reality. And you want, probably, your dominant poles to be inside this heart-shaped region to reduce your percent overshoot. If somebody says, I want a percent overshoot of 30%, they're telling you what zeta is. And zeta gives you a pretty big heart. And if you probably want to be 30% or less, that means you need to be inside that heart with your dominant poles. Is that clear? Now, if you want to be certain percent overshoot and a certain settling time, now what do you have? I'm getting ahead of myself, but now do you see what pictures you see or images you have? You now have, and again, I apologize for those of you that are listening, Maybe you can pick it up on the microphone. You can now hear what I was doing. I was drawing a circle, wasn't I? And you now have to worry about the intersection of these two constraints. A circle that gives you your settling time and your heart. And you now have to figure out the overlap pattern that's appropriate for your dominant poles to live inside. We're trying to find nice, comfortable places for your dominant poles. The intersection of these design constraints. All right, so let's do that now. Suppose we have the following. Possibilities. Somebody gives you a settling time and a percent overshooter specified. They give you both, and you have to meet both constraints. What do we know T settle leads to? That gives us a radius, doesn't it? Percent overshoot. And if you have 30 seconds left on your exam, and if you write heart, I might just have a soft heart and give you a half a point out of 50 extra credit or partial credit. But if you say heart, I'm probably going to start having a soft heart. But that's what you have when you have a percent overshoot, right? You have a zeta value, which leads in the Z-plane to a heart. All right. But now if somebody gives you that, your boss could care less if you're talking about hearts and circles, right? She's going to say, would you just cut it out and give me the answer? I don't care if you have a bullseye and a heart. Oh, now we have Cupid, don't we? All right, so now, sorry. Wow, you didn't know you were going to get this kind of a lecture. I didn't either. Let's find these poles, okay? Let's forget about Cupid. But this is actually the Cupid condition, isn't it? If I now on exam 3 say, okay, you have Cupid constraints, you know what I'm talking about. Settling time and percent overshoot. Hey, that's pretty good. All right, so now where are the poles? We now know that we have an R and a zeta based on settling time and percent overshoot. So we're basically given R and zeta, and we need to find a dominant pole pair. We have the conjugates, but we'll just look at one of those. We want to find an R and a theta sub D that are consistent with the R and the zeta. R is pretty easy. That's just R. We have that. Now we need to find theta sub D in terms of zeta, which is not a direct, but we're going to derive that. We need to find theta sub D given R and zeta. I mean, if you are good at drawing, you know zeta, you can draw that heart. You know the radius, now you know where those are satisfied, the intersection of those two curves, if you're good at sketching. I'm not, so I have to do it analytically. So let's derive this relationship. Here's our solution. We know we're given R, but we know how we can parameterize that in terms of natural frequency and damping ratio. We know that R is e to the minus zeta omega sub nt. We can take the natural log of both sides. And now we have a way of expressing omega sub n, our natural frequency, times t, in terms of R and zeta, and those are the two parameters we were given. So this now says that omega sub nt is minus natural log of R divided by the damping ratio, zeta, just solving for omega sub n cap t. But what is theta sub d? Theta sub d is omega, the damped frequency times capital T. That's how we define theta sub d. But omega sub d is omega sub n square root of 1 minus zeta squared. Let me just move those around a little bit relative to each other. And we now know what omega sub nt is in terms of parameters that we know, R and zeta. And we already know zeta, so let's just make that substitution. And we now know that theta sub d is this minus ln of R over zeta. That's the omega sub nt in front of 1 minus zeta squared, square root. Now, if you're given the Cupid conditions, settling time and percent overshoot, you can now find R and theta sub d and plot your dominant poles for those two upper values of settling time and percent overshoot. Is that clear? This now allows you to write down R e to the j theta sub d. Is that okay? So somebody gives you settling time and percent overshoot, you now know how to find your poles, z delta, at that particular constraint. You may have to relax or tighten those, but now you at least have 2 points. Really 1 point and its twin. What if you're given some other specs? Suppose you're given zeta, which is really, maybe they give you zeta indirectly by specifying the percent overshoot. So they may give you the percent overshoot. You can use that formula to solve for zeta. And maybe they give you theta sub d. We're going to find that that's actually related to the peak time. So let me say this. We'll show this relationship later. We're now given zeta and or percent overshoot and peak time. We now need to find what's missing. We still need to find these poles at z delta, which are R e to the j theta sub d. Well, we know what the angle is. We were given that if we're given the peak time. We can calculate theta sub d given the peak time, and we'll show that in a minute. We now need to relate zeta to R, and we'll do something similar to what we had before. But now we have theta sub d was given. That's omega sub dt, which is omega sub n square root of 1 minus zeta squared t. But that's just what we're writing as omega sub nt square root of 1 minus zeta squared. But now we can solve this, theta sub d equal to that right-hand side, in terms of omega sub nt, which we don't know. But we do know theta sub d and zeta. So we now know omega sub nt is theta sub d square root of 1 minus zeta squared. But we know what r is. R, parameterized in terms of damping ratio and natural frequency. And we know the damping ratio. We don't know omega sub nt, but now we have a formula for it in terms of theta sub d and zeta. So that we now know that we have e to the minus zeta, theta sub d over the square root of 1 minus zeta squared, or if you sort of write that a little bit cleaner, we have minus zeta theta sub d over the square root of 1 minus zeta squared. And now if somebody gives you zeta, which is percent overshoot, they give you peak time, that gives you theta sub d, now you know what your radius is, and you can plot r and theta sub d to give you your dominant poles. Questions on that? Let's now look at the time to peak. I said we would do that later. Let's do that right now. Now you know bullseyes and hearts. We have one more sort of constraint or geometric shape or condition to worry about with respect to a transient design spec. Which is the time to peak or the peak time. I may say it many different ways, but peak time or time to peak. And you know where that is now, right? From the answer to the joke, the end of the lecture, that's that peak of our percent overshoot. That's the peak time, where that occurs. That's our peak time. And we derived last time that that occurs at pi over omega sub d, with omega sub d in the S-plane being this imaginary component of your complex poles. And you could then solve that for omega sub d in terms of time to peak. If somebody gives you a time to peak, they've now given you your damped frequency. This is now pi over t sub p. In discrete time, we may be more interested in our theta sub d, the discrete time angle in the z-plane, and that's omega sub d cap t. Knowing what we now know, parameterized way of thinking of omega sub d, we now can just say that we have pi t over t sub p. And now if somebody gives you your peak time and you know your sampling period, capital T, you now know what your theta sub d is in radians. So if your sampling period was 0.1 and somebody says your peak time needs to be 0.7, then you know what theta sub d is going to be, what fraction of pi it's going to be. If we start comparing or in the S-plane, what's theta or what's omega sub d? Do you remember what omega sub d looks like in the S-plane? That's just the imaginary component of your poles. Your poles could be anywhere on this dashed line and they have the same damped frequency of oscillation. They have more damping the further into the left half plane you go, but they have the same omega sub d1. And if I give you j omega sub d sub 2 that's bigger, then what's your peak time? If I'm on the blue curve versus the red curve, which one has a faster peak time? Where do you want to be to have a small peak time? If you want a small peak time, what do you want for omega sub d? So you want T sub p to get smaller. What do you want the denominator to do? You want the peak, what did I say? Peak time smaller. So the peak time smaller, I hope that's what I was saying. Maybe I wasn't. Peak time smaller says you need to be bigger or more imaginary peaks. You want your omega sub d to get bigger. You want your denominator to increase, right? So as omega sub d increases, as you move up here with the imaginary part of your complex pole, you're speeding up your peak time. You're going to get there quicker, but your overshoot may go crazy. I'll use that word. That's okay. I was going to say something else, but I can't. So now, if you want to increase or to improve your peak time, make it smaller, you need your imaginary part to get bigger. So omega sub d sub 2 in this picture gives you a smaller time to peak. You get there quicker. Is that okay? And if you want little overshoot, where would you want to be on this red line? Can you have your cake and eat it too? Can you have quick peak time and small overshoot? What influences overshoot? Your zeta, right? And it's only a heart in the Z-plane. It's an angle in the S-plane. So if you want little overshoot, you want this pi wedge to get smaller, don't you? To improve your overshoot behavior. And I said a sweet spot would be a zeta value of 0.7 to give you a 5% overshoot. So if you know that you want this for your peak time and you want a nice overshoot, maybe you just make your real part the same as your omega sub d2 to get you a zeta of 0.7 or an angle of 45 degrees in the S-plane. That's a nice spot for peak time, settling time trade-off, because the further you go into the left half plane, the faster you are going to settle. And the better this angle is, the better your overshoot behavior, the less overshoot you have. If you have a really steep angle versus a shallower angle, the blue highlight is better than the yellow highlight in terms of magnitude of percent overshoot. Is that okay? Is that making sense? Now we want to translate, I've got too many curves on here. I could draw another one, and that would be this vertical line, and that's the settling time line. You would want to be to the left of some vertical line. That would be your settling time spec. And you could have all three active, and you need to satisfy all three at the same time. In the Z-plane, what do those horizontal lines, blue and red, look like? I am now replacing S with either j omega sub d1 or j omega sub d2. And what's going to happen in the Z-plane? I replace S with j omega sub d1, what do I get for, oh, maybe what I want to do is, actually what I want to do is not replace it with j omega sub d1. Let me think of not worrying about the j so much, but the theta sub d. I want now, I was misleading, I want theta sub d, which is omega sub dt, right? In my transformation, I want to know where's theta sub d in the z-plane. This one's easy, really. What's theta sub d? Theta sub d is an angle, and depending on the magnitude of omega sub d1, that influences the angle of theta sub d. Meaning, if I want the blue curve, that's, let's say, theta sub d1. Now, where's the red curve? It's a bigger angle. Now, time to peak, if we want to reduce the time to peak, now we need this angle to be bigger in the z-plane. We want to be above or beyond that angle. Is that clear? Which is consistent with what we had in the s-plane. So now, time to peak translates into an angle in the z-plane. Let's look at an example. Suppose the time to peak is 6 sample periods. What's theta sub d? Theta sub d is omega sub dt by definition, but we know how to relate omega sub d and time to peak, don't we? Time to peak is pi over omega sub d. We can solve that for omega sub d, and we get pi over t sub p times t. And now somebody tells us that the time to peak needs to be 6 of these capital T's. It's 6 sample periods. We now have pi over 6t t, or theta sub d if I go to degrees, which is maybe easier to think of. Now I need an angle of 30 degrees for my time to peak spec. I need my angle to be 30 degrees or bigger to achieve a time to peak of 6 sample periods. Now, theta sub d can also influence how many points we have in each cycle of the oscillation. So let me say also theta sub d can influence, or you can think of it as influencing, the number of samples per oscillation cycle. As an example, suppose that somebody says, oh, your theta sub d for a pair of complex poles is 60 degrees. That now says that the number of sample points per each cycle of oscillation is going to be, one cycle is 360 degrees, or 2 pi. It's going to be that value divided by theta sub d. So the number of points, sample periods per cycle, is influenced by theta sub d if we were in degrees. So now we have n equals 6 sample points per oscillatory cycle. Meaning if we had something that was doing that, a decaying exponential, let's say, and this is an interpolation between all of the possible sampling points, but now we're saying that with n equal to, or with theta sub d equal to 60, let's say this is now a point, and now we go one cycle, that would be over there. We need 6 points, so I'd go 1, 2, 3, 4, 5, 6. And that's how many points we would see. Those would be uniformly distributed. So now I have 1, 2, 3, 4, 5, 6, and that just keeps repeating. That's what theta sub d can also be interpreted as providing. Is that okay? Meaning if somebody now wants, well, let me just say this, or you could say of n sub d times theta sub d needs to be 360 degrees or 2 pi, where n sub d is our number of samples per cycle, and theta sub d is this z-plane angle. And what's actually happening, if you think about the mode of your response, it's influenced by z sub d. After one time step, you've multiplied your initial condition times that mode, r e to the j theta sub d, or r at an angle. So now you're, I don't know how to do this audio-wise, but you're now here. Then what happens? You square that to get to the next point. You've now, if your r is less than 1, you've collapsed your r, and you've moved to 2 theta sub d. So you're sort of spinning around in the z-plane in a way, collapsing, and your angle is getting bigger as you evolve in time, as n raises that z delta to higher and higher powers. Now, with this relationship, we can, if someone gives you, or if someone wants a particular number of n sub d samples per cycle, then they've actually given you theta sub d. They now have theta sub d as 2 pi over n sub d if they want theta sub d in radians, or if they wanted theta sub d in degrees. You now have theta sub d as 360 divided by the number of samples per cycle, n sub d. For example, if somebody says, I want 10 samples per cycle, you now know that you need a theta sub d of 36 degrees. Can we summarize what we've done in today's class so far? Meaning, if you're just now waking up, I'm not going to hold it against you. Maybe you had a busy night. You had somebody else's homework to do. Tonight you have mine, right? Homework is due tomorrow night. But if you now make a table of what we've just done, you could have a settling time spec. You could have a percent overshoot spec. And you could have a peak time spec. If somebody's kind enough to give you these 2 at a time, then you can pretty easily find your pole locations. If somebody gives you a settling time spec and a percent overshoot, that's our Cupid condition, wasn't it? That was our bullseye and a heart. What's your pole location? Well, they gave you R, they gave you half of it, but now we already derived what the theta sub d was in terms of R and zeta. Theta sub d was this minus natural log of R, zeta, that's supposed to be zeta squared, square root of 1 minus zeta squared. So now you have a way of finding z delta, given settling time and percent overshoot. What about another pair of numbers? Maybe somebody gives you settling time spec and peak time. Well, that's about as easy as it gets, isn't it? They've already given you R and theta. So now z delta is just R at an angle of theta sub d. Or, depending on if you wanted to write it as R e to the j theta sub d, our polar notation is saying that's what we're doing. Or, you have one more possibility of giving you these two at a time. Somebody could give you a percent overshoot and a peak time. Now you're already given half of it, theta sub d. You now just need to replace or write R, your radius, in terms of theta sub d and zeta, and we derived that. R was now equal to e to the minus zeta theta sub d over the square root of 1 minus zeta squared, and theta sub d you were just given. So now you have a table if you're given those two at a time. But exam 3, I probably won't be that nice. My heart might be a little bit hardened by that time, right? We're getting close to the end of the semester. You have exam 2 in a week. All right. Now, what if you're given these 3 at a time? What you probably want to do is pull out a napkin. Not to tear up into, but to sketch on. Okay? So now, I give you a percent overshoot. What do you see? This is the Z-plane. I've given you a percent overshoot. Now you have a heart, right? That's a zeta value. And you can reflect that across the horizontal line. I give you settling time. What do you now have? Settling time. Bullseye. So now we have this. I didn't draw that quite the way I want, but that's what we have. I have news too. We now have time to peak, right? Peak time. This is news for all of us, right? What's peak time? Angle, isn't it? So now we have this. Oh boy, which side and where are we living? Where do we need to be if we need to satisfy all 3 design constraints? Meaning, we want settling time to be some amount or less. That means we need to be inside that black circle. We want percent overshoot to be some amount or less. We need to be inside the blue heart. Should have used red, huh? Oh well. You can use red in your notes because That'll give you a red heart. Mine's blue. It hasn't been exposed to oxygen. I'm black and blue after this lecture. I don't know about you, but so we don't have the peak time spec, but now we have a peak time. Which side of that angle do we want to live on? If we want a peak time to be some amount or less. Can I shade where we need to be? A Z delta anywhere in that yellow shade would satisfy those design specs, and this is where it makes everybody nervous. Because you're used to having one right answer. There's an infinite number of points in that yellow shaded that could be correct, but there's some that are better than others. You probably don't want to have negative values, so you probably don't want to be to the left of that vertical line. So, and there's not much difference between, in my sketch, the percent overshoot and the settling time. But there could be. But that's where you would want to live in those particular constraints. And if you needed to relax certain constraints or start making certain constraints more restrictive, you know which things are going to happen. If somebody wants tighter settling time or percent overshoot, now that's going to be smaller, that blue curve. But where you want to be living is where they all three are satisfied. And that could be that yellow region. Is that okay? And I could word this on the exam to where, oh, I want your percent overshoot to be 10% or larger. Now you need to be beyond the blue and inside the unit circle if I want a stable response, and the other conditions, whatever those might be. We'll pick up at that point on Monday. Thank you for your patience.